Hi everyone, welcome to week 7. Okay, so we're kind of in the final couple of weeks here, and we've got I think 5 note packets left and 2 experiments. So the first experiment you're capable of doing right now, so I'll set that tomorrow. So look tomorrow for the pre-lab for that one. Okay, as I speak, it's what's the date today? Sunday the 12th. Okay, so this will go up tomorrow. Actually, this will go up today, and lab will go up tomorrow, and then they're kind of due one day later after those respective dates, if that makes sense. Okay, so moving forward, I want to kind of push on with the notes a little bit this week, probably get 3 packets done, and maybe 1 lab, right? So we'll see how we go. All right. Now then, as we saw in the last packet, the Schrödinger equation gives us some information about electron identity, essentially. Okay, so electrons, no two are the same in nature. That means they have a unique location, kind of, right? And then once in that location, they're either a spin up or a spin down electron. So we can have 2 electrons in the same place. And if you remember, when we did the whole points of a compass thing, electrons tended to travel in pairs, right? Why was that? Because those electrons traveling in pairs are occupying the same region of space, okay? So that whole points of a compass thing we did and pairing electrons up, that actually nods to this Pauli exclusion principle, this whole concept that electrons are unique. They have a unique address, and you can have 2 electrons in that unique address, but one has to be spin up and one has to be spin down, okay? So all electrons are unique. Now, we know this because, you know, having solved the Schrödinger equation, which perfectly models nature, okay, kind of tells us how it really is in nature, we have a set of interdependent numbers, okay? That means whatever the value of n, the so-called principal quantum number, the most important quantum number, it determines the ranges of all other quantum numbers, okay? And you know, there's some easy phrases we use: add a layer, add a shape. We'll get to that later, which will make questions very easy. But you can be the architect. You can use this math to basically map out the entire parking lot for an atom, okay, which we'll kind of do in a little bit, okay? All right, so quantum number interdependency, so allowed quantum numbers they call them, okay? So if it's a valid combination, it's allowed, it's the place where an electron can exist, right? So first one, as we saw, the distance quantum number, the so-called principal quantum number, is just simply the layer, okay? So if I look up here, obviously these electrons would be in layer 1, n equals 1, these electrons would be in layer 2, n equals 2. Okay, so n is the principal quantum number, the shell, or as we'll see later, it's often called an energy level when we get onto this level of sophistication, but it's really a shell or a layer. Okay, then we have L. L is the shape quantum number, okay, and it has the range of 0. If you remember before, 0 was a sphere, a range from 0 up to n minus 1. So as n gets bigger, the number of shapes allowed increases. That's why there's only 1 shape in the first layer. If I make n 2, 2 minus 1 is 1, 0 to 1, L equals 0 is a sphere, L equals 1 is a dumbbell, a P, L equals 2 is a fan, a D. Okay, and we see that over here. So that's our code. The higher the value of n, the bigger the range of L. So the whole add a layer, add a shape thing is here. That's what add a layer, add a shape looks like mathematically. Okay, now when we get those more interesting shapes, so a sphere, if you look at it from any direction, it looks the same, so it has that perfect symmetry, so it's really got only one direction. Okay, so that's what ML is. ML is direction, yeah. So ML goes from 0 to plus or minus L. So again, we're dependent on L, which is dependent on N. The further out you go, the more shapes, and therefore also the more directions. Okay, so when we have ML equals 0, all right, that's just one direction, right? And then we have, say, L equals 1, right? So that's those dumbbells. The range is from 0 to plus or minus 1 then. So it's minus 1, 0, plus 1, X, Y, and Z. So those dumbbells can go in 3 directions, okay? All right, so that's your distance, shape, and direction. They are all interdependent, and they depend really on the value of n. Remember the simple rule, the further out you go, the more stuff can happen, right? Add a layer, add a shape. as you add progressive shapes, the number of directions also increases. There's 1 for a sphere, 3 for dumbbells, 5 for fans, okay? All right, so you're like adding 2 each time. All right, and then the electron itself, as we mentioned before, thank you, Katy Perry, right? Electrons can be either spin up or spin down. There are basically 2 flavors of electron, right? They either align with or against the magnetic field. Male or female, up or down. Okay, 2 types. All right, so that makes them, you know, able to live in the same place because you can have 1 spin up and 1 spin down. Later on, instead of drawing little dots like this, we'll actually say that they're in an orbital and 1 spin up and 1 spin down. You may have seen that before. That's a spin pair of electrons, which in our dot diagrams is just 2 dots. Okay, so let's just recall. So down here then, recall the code for assigning quantum numbers. So 1s is a code, right? So those electrons in, let's go back real quick. Those electrons in helium are in the first layer, right? So the first layer is 1, that's the principal quantum number, that's n, all right? And then s is just the shape, right? And the code for a sphere is L equals 0, all right? So that's written right there, okay? So 1, n equals 1, s is really L equals 0. So the shape is a 0 shape, if you like, and the layer is 1. And that's the only available combination for the first layer, if you recall. Okay. Now, if I have a 2p, so the next layer I can have a 2s and a 2p. So I add shapes, right? So I keep the same shape I've established, so I can get s's and p's in layer 2, right? So I can have a 2p, n equals 2, L can be 0 or 1, right? If it happens to be 1, it's that dumbbell shape, right? Can you fill this one out? What's a 2s then? Okay, if a 1s is n equals 1, L equals 0, a 2p is n equals 2, L equals 1, what's a 2s? Well, n obviously is 2, and an L shape for a sphere, or code is 0. Okay, all right. Now, you can, if you wish, right, work this math out and figure out allowed orbitals, right? But I've got an easy method that works every time, and it's fantastic for exams, right? Okay, so remember the easy method, right? Add a layer, add a shape, right? So in layer 1, S only. Layer 2, S and P only allowed, right? Layer 3, S, P, and D only allowed. So if I'm in layer 1, I can only have an S. If I'm in layer 2, S's and P's only, layer 3, S, P's, and D's. So then you might get asked a question like this, right? And actually, here's the question. Which of the following represents an impossible combination? In other words, they're not allowed, right? Which of these are not allowed? Is there such a thing as a 1p orbital? Well, n equals 1, right? So L equals 0 only. We just talked about that. So in layer 1, there's only a sphere, right? So I can't have a p. So no. 4s. Careful here, right? In the 4th layer, I can have layer 1, S, layer 2, S and P, layer 3, S, P, and D. Layer 4, it actually goes alphabetical from there, right? We don't typically go there because it's some very rare and interesting elements that far down in the periodic table. But it's F, it goes alphabetical. So S, P, D, skip E, because that's for electron, and then F is the next orbital. There's some interesting shapes. They've got 7 directions. We're not going to talk about them in this course, but if you want to look them up in the book, F orbitals are interesting. Is there such a thing as a 4s? Well, of course, because there's an S in every layer. Okay, remember we talked about the balloon? 1s, 2s, 3s, 4s. It's just a big old sphere, right? And a balloon or a sphere starts every layer. Okay, so that's allowed. 2D or not 2D? That's the question, right? Can I have a 2D? Well, I can have an S in layer 1, an S and a P in layer 2, an S, a P, and a D in layer 3. Oh, it's telling me layer 2, right? So S and P only, so that's a no. No D's in layer 2. Okay, no D's in layer 2. All right, hopefully that makes sense. Remember the easy way to do it. Add a layer, add a shape, and you can just tell me real quick, is that allowed? No, only S's in layer 1. That allowed? Yes, S's in every layer. Is that allowed? No, D's from layer 3 onwards. Okay. All right, now then, remember I talked briefly in the last packet about how you can use that quantum number math essentially to be the architect of the periodic table and the architect of where electrons essentially park in atoms, okay? And that's what we're going to do right now. So let's be the architect, just like the guy from the Matrix, right? Okay, so this is what we call an energy level diagram. Okay, now don't be confused by this. It's actually pretty simple. So if you think about an atom, there's a nucleus, right? Then there's these layers of electrons, all right? What we're doing is we're just kind of zooming in. And we'll talk more about this when we talk about our lab this week, okay? Instead of having these kind of curved lines, we're just going to kind of straighten them out, all right? So imagine that down here, okay? So this is the nucleus. That's layer one. It's really kind of curved, isn't it, right? It's really curved, yeah. Yep. Move it up. So there's the nucleus. It's really kind of curved. We're just kind of making it life easy by making it kind of a flat line. So each line here is an energy level. Layer one, layer two, layer three. And interestingly, you know, I said, and maybe some of you kind of thought this was a bit weird, every atom has an infinitely large parking lot. Well, a philosophical question would be, well, why doesn't a single atom fill the entire universe if it's got an infinite number of layers? Turns out it's a bit like, you ever play that game where the wall is a certain distance away, right? You walk half the distance to the wall, right? And then you walk what's left, half of that distance to the wall. And then what's left, you walk half of that distance to the wall, right? Do you ever get to the wall? No, because you're asymptotically approaching it, right? So that's exactly what happens in atoms. So the first distance is really large, and then it's closer, and it's closer still. So the energy levels get tighter and tighter and tighter. And eventually they get to what's called a continuum, right? They get so close, they're hard to kind of tell apart, okay? And that's technically n equals infinity, which is the radius of the atom, okay? So that's there, so that's the radius of the atom, okay? Now, interestingly, energy is counted backwards in energy level diagrams, right? So because we never know, because every atom has a different depth, if you like, from the top to the bottom. So we can't really measure from the bottom. It's like saying, how deep's the well? Well, you measure from the top, right? So we'll see this in this week's lab. We actually measure energy from the top and we go minus, okay? So think of minus as a depth, right? So that's maybe minus 1300 kilojoules or something, right? Okay, per mole. Okay, all right, so that's energy level. That's why we call it energy level. It's really measuring how much energy it costs to pull the electron out. Okay, and just by convention, it's minus because we count from the top. All right, so let's do a little bit of a map then, okay? So kind of interesting. Here we have level one, right? So if I want to, I'll move that up for you. All right, here we have layer one. If I want to solve the Schrodinger equation, well, n equals 1, right? L equals 0 to n minus 1. And because n is 1, 0 to 0, therefore, L equals 0, okay? And then ML equals 0 plus or minus L, 0 plus or minus 0, 0 plus or minus 0 is 0, okay? So that means it's a sphere, and it's just one of them, one possible way it can look, right? So in essence, it's a small sphere, and that's our 1s orbital, right? If you remember our flower diagram, right? That's what I like to call it, okay? I can't seem to find my flower diagram, that's okay. Let's have a look over here. That's okay. So if you remember that one center sphere in our so-called flower diagram, there it is, okay? All right, so we solved the Schrodinger equation. We said, hey, you can, for layer one, you can be a sphere, and you're small because you're layer one, and you can only be a sphere because you have the one possible shape and the one possible look or direction. Okay, fair enough. N equals 2, think about that for a second. Well, we have L equals 0 to n minus 1, right? So just like before, it's a range, right? So I can have 0 or 2 minus 1 is 1. So I can have 0 or 1. Well, that's my sphere, right? It's a bigger sphere. That's my 2s, right? So I start the second layer always with the sphere, because I'm always going to have a 0 for L, right? How do I do the math? Yeah, it doesn't matter how big the number is. It's a range starting at 0, so always a sphere. And I go to n equals 1, which is a dumbbell, okay? So in layer 2, sphere and dumbbell. But wait a minute, now I've got 1 for n, right? So L will be the same for the sphere, right? Sorry, ML will be the same for the sphere. But ML equals 0 plus or minus L. When L equals 1, I got minus 1, 0, and plus 1. That's what we call x, y, and z in Cartesian, right? So I've actually got 3 different directions for the p's. So px, py, and pz, just like we saw before, right? Just like we saw before. All right, so I think I got a, yeah, there it is. Here's a classic slide, right? So there's 1s, That's the only thing allowed in the first layer. Layer 2, 2s, and then 3 different p's, right? So I can have one extra shape, but it points in 3 directions, right? Now remember, these are all superimposed on each topic, can't even say it, on top of each other, right? So it's like that center kind of expanding out. Okay. All right. Now, if I went up to here and had n equals 3, it would get a lot more busy, right? So if you want to do that level 3 math, you can. When you get to D's, okay, you'll see there are 5 combinations, okay? And what does that look like? I showed you the picture, I think, a while ago. Let's show you again. So D's are kind of weird. They look like this, okay? So there's 1, 2, 3, 4, 5 different directions for orbitals with this D shape, okay? All right, so L equals 2, so then 0 plus or minus 2, so minus 2, minus 1, 0, plus 1, plus 2 for ML, so 1, 2, 3, 4, 5 directions, okay. All right, not gonna talk about these too much, okay. Now, so we have those interesting shapes, right? Just looked at those, right? And if you remember drawing that flower diagram from the last packet, that's a complete pain in the neck to draw, and past about the second layer, it gets too busy to draw literally on top of it when you start kind of superimposing shapes on shapes on shapes. So instead of doing that, we use these energy level diagrams, which makes our life super easy, right? So instead of drawing a sphere or a dumbbell, we're just going to represent it by a box, right? So each box, this is the key fact today, right? So each box in an energy level diagram or an orbital box diagram, which we'll see later, which is simply an energy diagram tumbled onto its side, okay? Each square here is an orbital, right? So that's my 1s, okay? So instead of drawing a little sphere, I'll just draw a box, right? I can get 2 electrons in there, yeah, okay? Because hey, 2 electrons, spin up, spin down, occupy the same region of space. There's my 2s, okay, so that's my bigger sphere. And then here, look, we have 3 conjoined boxes. Now that's weird, right? They're called degenerate orbitals because they're the same distance from the nucleus. They're just pointing in different directions. So it's px, py, pz, okay, all right? And they're technically the same distance from the nucleus. They're in layer 2, okay? Layer 3, s, p's, and then the 5 d's, right? So each box, that might be the, you know, the x, y, z, y, etc., right? So these are the different directions, all right? So that's the architect's map of the periodic table, okay? Now what we'll do with this map, we'll just put electrons in. So say I was doing helium, right? How many electrons? 2, right? And they fill close to the nucleus. 1, 2. Hey, makes total sense, right? Remember I said, hey, we draw helium as a pair, 2 pairs, 2 dots as a pair when we talked about empirical models, right? Okay, that's because there's 2 electrons in the same region of space. They're both in that 1s. So 1, 2. That's how they exist, right? That's how they exist. So it would make no sense to put one over here because there is no other orbital for it to go into, right? They have to live in the same orbital, and that's represented by that, okay? If I did lithium, starting to get the hang of it now, right? It's 1 more electron. There it is, okay? 1, 2, 3. So we're literally filling the parking lot. We're literally filling the parking lot, okay? All right, so, you know, we always fill closest. Electrons are attracted to the nucleus, of course. So that's the Aufbau principle, building up. So fill the first layer closest, second layer, third layer. Okay. Now there is a bit of a complication. Okay, there is a bit of a complication which we'll talk about. Okay. So turn over. So let's just look at the hint here. So recall what each quantum number represents. N equals distance, L equals shape, ML equals direction, okay? MS is spin, right? And how they're related to each other, and that gives you their location in the energy level diagram, all right? Okay. Recall that each box is an orbital. Each box can hold up to 2 electrons, all right? So once you get 2 electrons in the box, it's full, right? Okay, and we'll talk about how we fill the boxes right now, okay? Now, this is where it gets interesting, right? Because we have this thing called Electron-Electron Repulsion, right? So if I try and put 2 electrons in the same region of space, they kind of repel a little bit, don't they? Because they're both negative, so they don't like it, if that makes sense, right? So this is why we do that points of a compass thing. Electrons only pair up when they have to, or if you like, enter the same orbital. They only enter the same orbital when they have to, because there's a slight electron-on-electron repulsion, okay? And that's kind of interesting, because what it does to our map is it actually moves some of these layers around, okay? So the analogy would be this. So imagine like going to Joule and you park your car in a spot, right? And then you park your car and the parking space moves further away from the nucleus, which is kind of weird, right? But that's what happens in multi-electron atoms. So anything past helium, we start putting electrons in that second level, we have the moving spaces, okay? And what does that look like? Well, if you've got the packet in front of you, keep this to the side, right? Just for reference. I'll flip over and I'll show you. So I want you to sketch this in the spot, right? So what have we got? We have, let's just do for the first 3 layers there. 1s is the same, and then 2s, actually, it's not so much that the p's go higher, it's that the s contract. So we have a contraction. The s's are actually squeezing closer as electrons fill the layers, right? So in order of filling then, because if you think about it in that last one, we had a bit of a toss-up, right? The 2s and the 2p in our simple diagram are the same distance from the nucleus, so I could have put that electron there without any problem because it's the same distance. It's not closer, it's not further away. They would be degenerate, but they're not, right? When we look at it, the s would now fill first, okay? And if you remember my flower diagram, the 2s looked a little closer than the 2p. It was on average, it was about the same, but the p is peripheral, it pokes out a little bit, okay? So 1s fills first, 2s, 2p, 3s, 3p, and this is why there's a weirdness in the periodic table, which we'll get to. The 4s actually sinks all the way down below 3d, which is kind of crazy, okay? So 4s fills before 3d, which we'll talk about, okay? So what I want you guys to do, sketch that, okay? So maybe I'll put it on the screen there, okay? So, just move it down there. You can just about see the 3Ds, right? Okay, so pause that and sketch it in the spot where you have room, okay? That's the spot, right? So if I did it, energy level diagram, energy level diagram, 1s, so that's n equals 1. I'll do it kind of to scale. N equals 2, 2s. And then I have those degenerate 2p. All right. Then I have 3s. Oh, that's not drawn very well. 3p. Okay, and then 4s sinks down here. 4s. And then, that's better. 1, 2, 3, 4. 4d. Okay. So what's the order of filling? What's the order of filling? What's closest? And we'll kind of, as you use this, it will become second nature. But 1s always fills first, then 2s, then 2p, then 3s, then 3p, then 4s, and then 3d. Okay, all right. We typically don't go past, that's 3d, right? We typically don't go past 3D in terms of our 101 examples, but if we did, I mean, you can look at the diagram in the back of the, I got it on the next page actually. We'll look on the next page to see what goes past 3D, but you know, there's a trick with the periodic table which I'll show you which allows us to do that very simply. Okay, so application 1 is just using the map now to write and fill out electronic configurations, right? So electronic configurations, filling the so-called parking lot. That's how we write an electronic configuration. So I'm actually going to pause here just for a second because I'm running out of time. Okay, I'll come back in a second. Hi everyone, welcome back. So our first application of quantum mechanics is electronic configurations. Okay, so you can kind of figure out where electrons are in any atom using the rules we just talked about. Okay, so remember the basics. We have this kind of infinitely large parking lot. The location of the parking spaces are essentially assigned by solving the Schrodinger equation, and we saw that kind of in kind of its simplest form for the first couple of layers in our initial energy level diagram. And then we saw that, hey, when we start parking electrons in spaces, that mutual repulsion between electrons actually moves the spaces around a little bit. Okay, now that concept is called Electro Dynamics. Okay, now that was a Nobel Prize for Richard Feynman back in the 60s. Okay, so if you ever watched The Big Bang Theory and they idolize Richard Feynman, that's his claim to fame. Okay, Richard Feynman. All right, so bottom line is Feynman kind of, if you like, added to what the architect did and actually kind of said exactly where the spaces move to when they start to move around a little bit for multi-electron atoms. Okay, so bottom line is that we have the parking lot. Okay, we have the parking lot, and we're just going to fill it. Okay, so there's some very simple rules for filling the parking lot, or as we'll say, writing electronic configuration. So we'll kind of put little electrons in the map, and we'll convert that to like a little sentence, a little kind of summarized version, which is called an electronic configuration. Okay, so the basics remain the same. So a lot of this kind of carries over from the dot diagrams. First things first, the number of electrons attracted, so to speak, is the same as the number of protons. Saw that before. Hydrogen has 1 electron. Why? It has 1 proton, atom to neutral. Carbon has 6 electrons. It has 6 protons, atom to neutral. Okay. All right. Aufbau principle. The electrons get as close to the nucleus as possible because minus is attracted to plus, right? So we fill the closest layer first, second layer, third layer, fourth layer. So we fill in order of closeness. That's called the Aufbau principle. Aufbau is German for building up. Okay. Next couple, a bit more new model rather than old model, okay, but they do explain things we see in the empirical model. So electrons only pair up when they have to, that whole kind of 30-something New Yorker thing, okay? That's because of what we call Hund's rule, because electrons are both negative particles, right? So it's like trying to put 2 negative charges into the same region of space, right? They're not going to like that. They're going to have a certain amount of mutual repulsion, okay? So it costs a little bit of energy to spin pair electrons, as they call it, okay? So when we put electrons into the same orbital, the same little area, there's a slight bit of repulsion between them, and it costs a little bit more energy to get that second one in there. Okay, that's why we do points of a compass. If you think about points of a compass, it's all single electrons, right? And then we pair it when we have to, because it costs a little bit of energy to pair an electron. Okay, that's called Hund's rule. Electrons only pair it when they have to is actually called Hund's rule. Okay. It's kind of related to the one we've been talking about, Pauli exclusion principle. We said, hey, we can only get 2 electrons per orbital because electrons have to be unique. They can live in the same orbital, they just have to be different, all right, spin up and spin down. All right, now, the map, I'll show you a big trick in application 2. But if you just want to look at this order of filling, this is the bigger map, if you like. So I showed you the first 3 or 4 layers on the first map, but then you have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4s, 5s, 4d, and that's the order of filling. We just follow it through, right? You do not have to memorize that because it turns out that's the same order as atoms appear in the periodic table. Remember how dot diagrams related to periodic table? Order of filling also completely describes the periodic table, okay? So I save it till last, and we actually don't have to memorize the order of filling. We can actually just use a periodic table, okay? But you may have seen this before. This is kind of the cheating way to do it. I'm just going to mention it. But if you kind of arrange the orbitals in this order and then just write diagonal lines, that gives you the order of filling. To be honest, this is unnecessary. You don't have to do this or this if you have access to a periodic table, which again we'll talk about in application 2. All right. So now we have it, all right? So what I've done, if I just show you, so I've taken the energy level diagram, the first 3 or so kind of layers, and I've repeated them here, okay? And what we're going to do is just fill these energy level diagrams for certain atoms, okay? So I've got nitrogen, fluorine, phosphorus, and chlorine, okay? Now, all you have to do, and if you can see, I've put like the atomic number there. So if you remember, you complete atomic symbol. Atomic number is 7. So 7 protons, therefore 7 electrons. So there'll be 9 arrows down here. Sorry, 7 arrows down here. I just glanced over at this one. Fluorine, element number 9, there'll be 9 arrows in this one. Phosphorus, there'll be 15, and chlorine, 17. Okay, so let's get to it, right? So all we're going to do, we're going to follow the rules. We'll fill from the lowest, okay, and get higher. All right. And a few little things come in as we go, okay? So Nitrogen, 7 electrons. Well, we're going to fill the 1s first, right? Okay. 1. Now, where's the next one going to go? This is too far away. It's going to, the little spin pair energy needed to put it here, that's much less energy than this gap here, okay? So we're going to spin pair, okay? We call that 1s1 and 1s2. That is actually the electronic configuration, if you think about it, of helium, right? 1, 2 electrons, so 5 to go. Next one goes here. Now the $64,000 question, where does the next one go? All right, interesting question. This is an energy gap, right? It costs energy to get up here. It's further away, so it's going to go here, all right? 1s1, 1s2, 2s1, 2s2. That's the code, right? Okay. That would be the fourth element, which would be beryllium if you looked in the periodic table. Now we go up here. We've got 4, 3 to go to make 7. Now we go here. 2p, one of them. Where's the next one go? Is it going to go next door or is it going to go this one? Now remember, these orbitals are degenerate. They're the same distance from the nucleus. For the same reason that this stayed here rather than going to here because of the gap, this will go here because it's the same distance. It's no further up, right? So when you have degenerate, it goes across 1, 1, 1. Remember, that's Hund's rule. Electrons only pair up when they have to. If this is the same distance from the nucleus as this box, it costs energy to spin pair them, so I'm going to go here. Right? It's a bit like having a, when you drive your car to Joule, there's some spaces in the third row, say. Do you park your car next to the junker car or one space over? It's the same distance to the store. It doesn't matter which space you choose. But you're not going to park next to the junker because you know someone will come back and open the door and scratch your car, right? That's electron-on-electron repulsion, so you go to the next space over. So one more. 1, 2, 3, 4, 5, 6. One more. 7. So that's the electronic configuration of nitrogen. We've got 2 on the first layer sphere, 2 in the second layer sphere, and then 3, 1 in each dumbbell, right? So remember, there are 3 dumbbells, 1, 2, 3, X, Y, Z, all right? Now, let's look at the nitrogen dot diagram real quick. Okay. Follow the empirical rules. What do we see? We see 2 on the inside. Boom! 2 on the inside. We then see a pair in the second layer. We see a pair in the second layer. Then we see 3 singles. Man, the dot diagram exactly matches the energy level diagram. That's empirical. That's how it is, right? You see how this accidentally perfectly matches this? That's why dot diagrams work. Awesome, okay? All right, now, if you got that, fantastic. Try putting in 9 for fluorine, 15 for phosphorus, 17 for chlorine, right? So you can pause and then do it, right? Okay, or you can just follow me, right? So I'm gonna go. So let's take a look. So fluorine 9, 1, 2, 3, 4, 5, 6, 7. 2 more to go, right? That gap is too big. It costs me too much energy to put it all the way up there, right? So I'm always going to spin pair them if there's a gap, right? But these are degenerate, right? So it's got to go there. And then the next one's got to go there. Okay. 2, 4, 6, 8, 1 more, 9. What does fluorine look like with a dot diagram? 2 on the inside, and then 7 on the outside, column 7, right? Does it match? 2 on the inside. Boom. 2. Boom. 2 pair. Boom. A single. Oh, yeah. Yeah. It absolutely matches, right? So you'll see why these are great models. They were constructed in an empirical way, but they absolutely model what's actually happening. Cool. All right. Now, phosphorus, if we look at it, phosphorus, if I find my periodic table, I didn't choose these by accident, right? So phosphorus is right under nitrogen, so it's going to have the same valence configuration, just 1 more full layer. And chlorine's right under fluorine, so it's again 1 more full layer, same valence. So they're going to have the same chemistry, right? And we'll see they have the same configuration. Let's see how that looks in the energy level diagram, okay? So 15 for phosphorus, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be neon, right? If you think about it, I failed like layer 2, right? And that's, That's neon, end of the second row. Right? So 10 and then 5 more. 1, 2, 3, 4, 5. Look at its valence layer compared to nitrogen. It's the same, right? The chemistry of column 5, the nitrogen group, is 2 electrons in the sphere and 3 electrons, 1 each in dumbbells. More sophisticated, right? It's got the same Lewis, yeah, because it's going to have the same outside, but it's got 1 extra layer. So let's just draw it, right? So phosphorus, 2 on the inside, that's those guys. And then second layer is 8. So if you like, that's 4 pairs. 1, 2, 3, 4 pairs, right? In the valence layer, column 5, row 3, a pair and 3 singles, just like nitrogen. So I think I said when we did our empirical models, the chemistry of column 5 is a pair and 3 singles. That's true for dot diagrams, so it's actually the chemistry of a pair of s electrons and 3 single p's. That's what it is. Okay. Finally, chlorine. 2 layers full. Let's quickly do that. Let's kind of do the mirror image over here. 1 layer. 1, 2, 3, 4, 5, 6, 7, 8. So that's neon. That's that, right? And then I got 7 more. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Valence layer, 3 pairs in a single. Valence layer for fluorine, 3 pairs in a single, right? It looks just the same. Awesome. So, key question at the bottom, do you notice any similarities? Yeah. That's the whole point, right? So the whole point is you should notice similarities between the proper model of nature, the energy level diagram, and the empirical, the dot diagram. Okay. Note of caution, dot diagrams and energy level diagrams don't work 100% of the time. I'll show you a couple of exceptions when we get to them. Okay, but for now, just take it for granted that, hey, dot diagrams and energy level diagrams match. Okay, so they're both modeling nature at different levels of sophistication, essentially telling you the same thing though. All right. Now, so interesting, right? So we have these energy level diagrams, right? There they are, right? Okay. Obviously, that could be a bit of a pain in the neck to write that entire kind of from the ground up picture every time. It's nice, right? It gives you a lot of good information, but it's time consuming. Okay, so there must be a more convenient way to do it, and there is. And I kind of mentioned it before, right? So what we're going to do, because we know the order of filling, we fill from the bottom up. So 1s, 2s, 2p, 3s, 3p. Instead of kind of having them go vertical, right? I'm just going to topple this over, timber, right? And I'm going to have them lie down in a straight line. Okay, so it's the same order, they're just now horizontal rather than vertical. We can do that because we know the order, right? And all I'm going to do, I'm going to call it an energy level, this is an energy level diagram. This is a orbital box diagram. Orbital box diagram is an energy level diagram lying down. Okay, so let's just do it for oxygen, right? So oxygen, element number 8, right? So 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. If I want to do its dots real quick. 2 on the inside, 2 pairs, 2 singles. Fantastic matches, right? Now all I'm going to do, I'm just going to kind of tip this over and do the 8 electrons. Aufbau. Let's do it in German. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I'm from Europe, all right? Okay, so 2, 2, so 1, 2, 3 pairs and 2 singles, 3 pairs, 2 singles. It's the same, right? It's the same. Make a little note there. This is exactly the same as this. It's just lying down. All right. Okay, if you want to try a couple more, you can. You could try lithium, you get that. And if you did carbon, you get that. Okay. So, we're going to practice a bunch of box diagrams, of course, right? But if you ever get stuck, a box diagram or an orbital box diagram is just simply an energy level lying down. It retains all the good information of an energy level diagram. It's just in a more condensed form. Okay. Now, a few more examples then. You can look at these at your leisure, okay? So there's lithium, 1s2, 2s1. Now, what we're going to start talking about is an even more condensed way to do it, right? An even more condensed way to do it, all right? So the electronic configuration, which this is, and I showed you like a kind of real brief introductions to what electronic configurations were in the first of these two packets, right? Okay. We can actually turn this box diagram, instead of a little map here, we can turn it into a set of directions, okay? So we can make it even simpler, right? So if I look at lithium, right? So let's just do lithium up here just to show you, right? So if I have lithium, right, I can draw my boxes as the same as the order we've established, right? So lithium, 3 electrons, right? 1, 2, 3, right? Now, what is that as an electronic configuration? Well, how many electrons in this 1s orbital? Well, there's 2 in there, right? So that's 1s, 2. How many electrons in this 2s orbital? 1 of them, 2s1. These are occupancies. How many electrons are in that orbital, right? Okay, makes sense, yeah? So there we go. So lithium, that's better, right? Lithium, 1s, and there's 2 in there, 2s is 1 in there. If I did my energy level diagram, my dot diagram, I got that, right? Okay. Now, if I do something a little bit more complex, and there's some examples right here. Let's just run down to nitrogen, right? Nitrogen, because we just did it, right? So nitrogen, let's move that up. Can I have this on the side looking at it, right? So it's going to be 2 in the 1s, 2 in the 2s, and 3 in the 2p, right? Okay. So let's do that. 7 electrons. 1, 2, 3, 4, 5, 6, 7. How many in the 1s orbital? 2. How many in the 2s orbital? 2. How many in the 2p? Now this is degenerate. We don't count the boxes individually if they're linked. We count them all together. There's 3 collectively in the 2p's rather. 3 collectively in the 2p's, so 3. If you think about it, each arrow is an electron, and the number of arrows is really this number, right, in each orbital. So if I count the electrons, it should be 7 because that's element number 7, right? 3, 4, 5, 6, 7, yeah. All right. Okay, so the sum of the superscripts is the total number of electrons in the atom. You know it's nitrogen, so that number should come up to 7. Okay, all right. Make a note of that if you wish. All right, so hopefully you're okay with tipping over the energy level diagram to make an orbital box diagram. And then because you know the order of filling, right, you can fill out the orbital box diagram in the same way you did the energy level diagram. And then just count how many electrons are in each kind of box, right? Okay, and you can write configurations. All right. Now, here's an interesting analogy, right? Remember we had this, right? So I did nitrogen again. Nitrogen is kind of a good one, right? If I do nitrogen, that was its full box. That was its full dot diagram, and this, if you remember, was its Lewis, right? That's all the electrons. That's just the interesting ones, the ones on the outside that do the chemistry, right? You can do a similar kind of thing. If you think about it, those are the 2 on the inside, right? So this core, we've seen it before, it looks like helium, yeah? So nitrogen has the helium core with the second layer electrons on top of that, right? So the helium core is the first full layer, okay? How does that correspond to something like silicon? Let's do silicon real quick, right? So if I got silicon, right? 2 on the inside, and it's kind of row 3, column 4. Second layer is full, and then 4 on the outside. So that's silicon, fair enough. If I did its Lewis, we did this before, I think, it's that, right? Okay, so I've got 2 full layers. That's 10 electrons. That's neon. That's called the neon core, right? If you think about it, that's everything to fill the entire second layer with third layer on top. So here we go, right? So if I wrote out the electronic configuration, this would be it, yeah? All right, but look, 3 is a principal quantum number. That tells you when the outside layer starts. So layer 1, layer 2, layer 3. Layer 1, layer 2, and then 4 on the outside, layer 3. So the electrons with the highest principal quantum number are valence. Everything else is therefore underneath is core, right? What core has 2, 3, 4, and 6, 10 electrons? That's the neon core, right? So in a similar way to how we turn dots into Lewis, we can just say, hey, that whole lot, just represent it with the neon sign. There it is. Okay, so you can sub the full underlayers for what noble gas it looks like, and that's called a condensed electronic configuration. To be honest, I don't mind if you do this one, this one. You want to write the whole list, and for heavy elements it can be a lot, right? Or you can write the inert core with just the valence on top, okay? It's like the difference between a dot and a Lewis, okay? So practice that, right? Practice that. You can write magnesium 2 ways and potassium 2 ways, okay? So it might be, okay, so there's a couple of ways to do it. You can either do the orbital box diagram and translate it to an electronic configuration, or as you become familiar with this, you'll be writing configurations really easily. And when I again show you that periodic table trick in the next part of this packet, it's dead easy, right? But for now, you know, do whichever one is more comfortable, right? So magnesium, all right, let's just think about this. Magnesium is element number 12, correct? Okay, so element number 12, so I've got 1s2, that's 2 electrons, and then I know it's 2s2, that's 4 electrons, and then 2p6, that's 10 electrons, right? That gets me to neon, and then 2 more, 3s2. Fair enough, right? That is the same neon core as here, right? Because I've got 3rd layer valence, yeah, just got less of them than silicon. Silicon and magnesium, both in row 3, right? So I'm going to have magnesium, neon core, 3s2. Okay. All right. Finally, potassium. If we find it in the periodic table, this is a trick which will kind of coalesce as we go. Potassium is in row 1, 2, 3, 4. So it's the first element in the 4th row. So it's actually going to be 4s1 as its last electron. We'll talk about that in a second. All right. So I'm going to have to get all the way up to argon. And argon is, if I look up here at my configurations, if I fill the 3rd layer, 8 electrons, 2 and 6, right, makes 8. So 3rd layer full, this is argon, right? So let's just do the whole thing. Potassium, it's going to be 19 electrons, right? So 1s2, oh, move up so you can see it. 1s2, that's 2 electrons. 2s2, that's 4. 2p6, altogether 10. 3s2, that's magnesium, that's 12, right? 3p6, 18, right? That's the end of the 3rd row because argon has 18 electrons, okay? And then one more, 4s1, okay, 19, element number 19. That is the argon core, 3 full layers, right? So it's potassium, argon core, 4s1. Awesome, all right. All right. Now, there's a few special things that go on, all right, okay. Transition metals, and we learned a few from our ions, right, so chromium, iron, silver, things like that, okay, things from that middle of the periodic table. These are called the transition elements because they transition from the left to the right. It's that simple, okay. Transition elements have d orbitals, all right, so anything post-calcium has d orbitals, yeah, okay. If you look at the periodic table, and this will become, again, clearer when we talk about the periodic table in more detail next application. So up to calcium, I haven't hit the transition yet. This is where d orbitals start to fill. So the transition elements, it's when we start putting electrons in the d levels, right, okay. And when we start doing that, interesting things happen, right? So let's just read these questions. Transition and other heavy elements or ion configurations, right? So the d orbitals of anything post-calcium belong to the core. Why? Because if you remember, the order of filling was 4s and then 3d, okay? Oh, look, in terms of quantum numbers, what's going on? The outermost layer is by definition the valence layer, right? Because 4s has slipped down, interesting, right? Below 3d, it will fill first, even though it's addressed to a higher level. And that's why the transition metals are such weirdness in terms of their chemistry, right? Because the valence layer is actually the 4s, which fills before the 3d. So we actually have, after we've filled the 4s, we start filling that 3d up to 10 electrons, right? Up to 10 electrons are actually subsurface, if it makes sense, from a address point of view, right? Okay. So that means we have partially filled pseudo core electrons, right? Which is kind of interesting. All right. So if we look at our order of filling, right? Actually, let's just flesh this out a little bit. The d orbitals of any post-calcium element or ion, by definition, belong to the core. Why? Because the valence layer has the highest principal quantum number, i.e. 4s, right? Okay, so 4s fills before 3d, so therefore anything post-calcium, those Ds technically belong to the core, right? So they're not full layers necessarily, but they are trapped underneath, okay? And that gives them super interesting chemistry, right? If we look at germanium, right? If we look at germanium, and it's kind of an interesting thing. Let me just do a little picture here. Okay, so germanium is element number 32. GE, right? 32. All right. Okay. So the order of filling is 1s, 2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now how do I know that? Because I'm just glancing back to my order of filling chart, okay? So 1s2, 2s2, 2p6, 3s, etc., right? And I keep going up, all right? Now, I look at germanium in the periodic table. It's in the 1, 2, 3, 4th row, right? So I'm going to need addresses up to the 4th layer. That's good, right? Now it's element number 32, all right? So I want 32 electrons, yeah? I need 32 electrons. And if we look back here, okay, 2 plus 2 is 4 plus 6 is 10, 18, 19, 20, 30, 32, right? So we'll go all the way up to 4p2. So that is the germanium electronic configuration, right? 30 electrons in the order of filling, right? Okay, but look, these guys are in the 4th layer. That filled before this, and then this filled afterwards, because that's the order of filling, right? Okay, these guys are valence. How many valence electrons are there? How many valence electrons are there in germanium? How many electrons in the 4th layer? If you said 2, if you said 2 and 2, 4, you're right. Where's germanium in the periodic table? Column 4. Ah, so those Ds, even though they're trapped underneath, because they're not valent, they don't interfere with our dot diagram, so to speak, right? Because germanium's still in column 4, still has 4 valence electrons. Okay, yeah, it's complicated. These things complicate things. Oh, there's my timer. Got 30 seconds left. These complicate things, but as long as we remember that, hey, 4th layer is valence, it's got 4 electrons. Therefore, we can think of these as part of the core, right? So think of it as a pseudo core, right? Okay. All right, now, real quick. Zinc has this configuration, and zinc makes a +2 ion. As you know, it will lose those 4s electrons. So that's zinc 2+. Okay, stop there because I'm about to run out of time. We'll start again in just a second with bromine. Okay, see you in a second. Okay, so left it there. I felt a little bit rushed at the end there, you know, trying to beat the timer. Which reminds me, start the timer. Okay, so bottom line is, in literally 5 minutes, you're going to see a trick that makes this seem trivial. Okay, but for now, all we're doing is we're creating energy level diagrams using the order of filling, tumbling them on the side to make the orbital box diagram, and then converting that to a configuration. Okay, all right. So see if you can do it for bromine. My suggestion is look at where bromine is in the periodic table. Okay, it's element number 35. Okay, bromine is element number 35. Okay, and then take a peek at the order of filling. Yeah, okay, take a peek at the order of filling. It's 2 electrons per orbital, right? So 2 in there, and then 2, 2, 2, etc., right? And you're going to add 35 electrons, right? And as a little hint, bromine is in row 1, 2, 3, 4, right? Bromine's in the 4th row. If you like, if you've got germanium, it's actually 1, 2, 3 electrons more than germanium, hint, hint, right? Okay, but you can follow the order of filling, and you get to bromine with 35 electrons. If you follow the order, you can write the electronic configuration. Okay, all right, so let's do it. So bromine, now I write it out longhand to start, right? So my order of filling is 1s2. I'm just following this kind of 1s2, I'll get 2 in there, right? 2s2, that gets me to there. 2p6, 2, 4, 6, right? 3s2, 3p6, all right? Now I know germanium's in the 4th row, right? So I'm going to get to the 4th row. I'm going to write those, yeah? So 4s2, and then 3d10. Let's just double check how many electrons we got now, right? So I'm up to here, right? So 2 and 2 is 4, and 6 is 10, 18, 19, 20. I got 30, right? So I need 5 more electrons. What's the next one to fill? 4p, up to 6, but I'm having 5. There we go. That's it. Okay. Now, what is the core? What is the valence? Well, valence is layer 4 onwards, right? So that's the core. Everything up to 3p6, which is 3 layers full. End of the 3rd row, argon, right? End of the 3rd row, argon. Okay. So I can write, as an abbreviation, argon, 4s2, 3d10, 4p5. Now that's part of the core. Sometimes, and I don't mind which one you do, it's just assumed that those 3d10 are in there, and we can write this instead. Okay, that makes sense, right? 4th layer, 5, 6, 7 on the outside. Bromine, 7 on the outside. There's its Lewis, right? Boom. Okay. Now, it gets even more interesting when we do things like iron. Okay. If I do iron, okay, Fe. Now what I'll do for iron is, okay, if I look at what iron is in the periodic table, it's the 1, 2, 3, 4, 5, 6. 6th one along in this block, right? So that, for reasons we'll talk about in a second, it's got 6d electrons. So it's going to terminate 4s2, 3d6, right? So what I'm going to do is do iron with argon, all right? And then 4s, 3d. Watch what happens here, right? And then 1, 2, 3, 4, 5, 6. That equates to 4s2, 3d6, which is argon, right? Okay, sorry, argon with these extra electrons. So that's iron, right? Now, do you remember what charge ions that iron made? Okay, it made a +2 and a +3. And at the time I said, well, just memorize that iron makes a +2 and a +3, and it gets complicated with transition metals, I said. Okay, you just have to learn these charges. But think about it, right? What are the valence electrons? 4th layer, so they go first, right? So so right now I've got Fe, Ar, 4s2, 3d6, right? When those two go, I get Fe2 plus 4s0, 3d6, right? Okay, so that's the configuration. When I lose 2 electrons, that's the +2 ion, right? Now look here, remember that electron repulsion for electrons in the same region of space? That's easily kicked out of there as well. So I can lose 1 more, I can lose 1 paired electron from in here, 4s0, 3d5. So that's why iron has +2s and +3s because it loses its 2 valence electrons to make this guy, and it loses this kind of weakly held, if you like, spin paired electron to make this guy. Okay, so iron makes a +2 or +3. And you know, transition metals have some various kind of combinations of electrons in the Ds, which can be removed to make what's called a half shell stability, right? So if I got 1 in each of these boxes, it's more stable than if I got like 1 or 2 just hanging on, right? Because they're spin paired. Okay, interesting. And one other thing that's interesting about iron, did you ever think about this? What's iron used for? It's used as a magnet, right? Remember magnetism? Okay, remember we talked about spin up and spin down. That was aligned with or against the magnetic field. So an electron that aligns with is magnetic. One that goes against is magnetic in the other direction. They cancel. Look here, if I've got a lot of unpaired electrons that aren't cancelling magnetically, that has a net magnetic moment, okay? So iron is a magnet because all these extra single electrons. That's what leads to magnetism. That's called paramagnetic. So if anything's paramagnetic, it's got lots of unpaired electrons. If anything's dimagnetic, it's got literally no unpaired electrons. They're all paired up, right? Okay, so that's why transition metals, those with d orbitals, are usually magnetic, because they have the capability to have lots of unpaired electrons. All right, so that's great, right? Now, application 2, the big application, okay? Now, remember I made a big fuss about doing those dot diagrams in the arrangement of the periodic table, okay, in the last packet, all right? And I showed you at that time that there's a correlation between battleship analogy, right? Rows was number of layers and columns was number on the outside, yeah? And that worked up to calcium because we didn't have any d electrons yet, right? Okay, turns out that when you look at it with a box diagram, you can model any electronic configuration in the periodic table just on the location of the atom, right? So it's a more sophisticated battleship, that's all it is, right? So here's the big thing, all right? So construction of the periodic table. Now remember, the periodic table's shape is derived from chemistry. Chemistry is derived from electronic structure. So the electronic structure essentially built the periodic table, okay? So let's look at that relationship in more detail, right? So the relationship between the arrangement of an atom's total number of electrons and its position in the periodic table is currently understood with the empirical model. We think about battleship. Carbon, column 4, row 2, 2 layers, 4 on the outside. Fantastic, right? Okay, but now we have a more sophisticated version, right? All we're going to do is what I call read across the periodic table. We know the order of filling, right? Okay, so it's 1s2, 2 electrons in the sphere. 2s2, 2 electrons in the sphere. 2p6, 6 electrons in dumbbells. Okay, now that order of filling is exactly matched by the periodic table. Okay, here's the big thing. Did you ever wonder why there was a 2 wide block at the beginning of the periodic table? Because what happens at the start of every layer? You fill a sphere, right? How many electrons go in a sphere? 2. 1 electron, 2 electrons, right? So this S block, this is called the S block in the periodic table. This is why helium, although it's written there, should really be written here, okay? Because I've got 1 electron in the 1s, 2 electrons in the 1s. It was put there because of its chemistry. It was put there because it's got the chemistry of a full layer. In some periodic tables, it's placed here because it has the electronic configuration of an S block element. Extra credit. Find me a periodic table where it's written here. Find me electronics, find me a periodic table, send me a picture where helium's here. Okay, that's probably a modern periodic table. Modern periodic tables constructed from electronic structure, 1s1, 1s2, right? Okay, and then if you think about the order of filling, 2s1, 2s2, or in the second layer, 2 wide block, 2s1, 2s2. As you saw with lithium earlier, its last electron was 2s1, beryllium would be 2s2, right? And then we go across here, and then we have this 6 wide block. Why is the block 6 wide, and why is it called the p block? Because I'm putting electrons into p orbitals, those 3 dumbbells, right? 3 dumbbells, 2 electrons per dumbbell, up to 6 electrons. So this p block is necessarily 6 atoms wide, because every time I add an electron here, I'm adding to a dumbbell, and I'm going around points of a compass, right? Okay, so the p block is 6 elements wide because I got 3 dumbbells, 2 electrons per dumbbell. Now if we keep with our order of filling, 1s1, 1s2, 2s1, 2s2. I'm just reading across the periodic table. So if I stop there, that would be carbon, right? Carbon is 2p1, 2p2. Its last electron is 2p2. Okay. 3s1, 3s2, 3p6, 4s1, 4s2. Now that's where we stop with our dots. Now remember, and this is the key thing here, remember the energy level diagram sunk down, right? So the S came before the D for 4s and 3d, right? So the 3d should be here, right? 3d should be in the third row, and that, if there was no electrons in the atom, that would be true. And the fact that, hey, add a layer, add a shape would hold exactly true, right? So first layer, S only. Second layer, S and P. Third layer, S, P, and D. It's labeled third layer, and that's where it's labeled quantum mechanically, right? Even though it starts to fill in the fourth layer. So it should be here, and it would be for an empty atom. But when we start adding electrons, that bad boy slips down. I think I just called it a bad boy. Don't know why. Okay, but the bottom line is this. That's that weird quirk in the periodic table I mentioned, right? So the 3d fills after the 4s, even though it should be a third row filler, right? Okay, because of this slipping down from multi-electron atoms. So the order of filling is the same as in the periodic table. Bottom line, when you do this reading across, and we just talked about iron, right? So 3d, 1, 2, 3, 4, 5, 6, that's iron, yeah, because it's the sixth one along in the 3d. So 4s2, 3d6, right? 4s2, 3d6, yeah? There. So we're just reading along the periodic table. Always remember, just read across, all right, to where the atom is. 3d in the fourth row, D slipped down one, F slipped down one as well, but they don't start till later, so we generally don't talk about them. And then when we come across, we go back to 4, right? So 4s, 3d, 4p. Okay, and that, if you just read across, that is exactly the same order of filling as we see here. So as I mentioned, this is the big trick. You don't have to remember this because it's the same order as reading across the periodic table. You'll always have access to a periodic table as long as you know that this is the S block, the P block, and the D block, and the D's are one less than they should be. You are fantastically fine, right? Okay, all right. Oh, extra credit, yeah. Periodic table. All right, we'll make that. I'll make this work. I'll make this due on Tuesday, right? No, I know. Okay. Okay. Now, so what we've got to do, if you want an electronic configuration, all we have to do is read across the periodic table. Yeah. Okay. Now you will have this one, so I'm going to recommend you use this one to read across, right? And I'm trying to kind of get it on. It's kind of tricky because it's the wrong size. So I use this one, right? So have this one just sitting there, right? Just look at it as I look at it, right? So I'm going to read across. I'm going to do chlorine, right? Chlorine is here, yeah? So it's the seventh one over in the third row, right? But if you think about it, it's 1, 2, 3, 4. It's the fifth one over in the 3p area, in the p block, third row. It's the fifth one over, so its last electron will be 3p5. So that should be the, you know, if we fill up to 3p5, that'll be chlorine, right? So let's do it. So watch how I read across here, right? Okay. So 1s1, 1s2 gets us to helium. Let's write this down. 1s2. 2s1, 2s2 gets us to beryllium. And we've got to do it blockwise, right? So these are called subshells. So I'm filling the s orbital. It's called S and P are in the same layer, layer 2, but they're different, right? So they're called subshells. And then the next subshell is 1, 2, 3, 4, 5, 6. That gets us to neon. So 2p6 fills that second layer and gets us to neon. That's the core, right? And then we're in the correct valence layer. 3s2 gets us to magnesium. And then 1, 2, 3, 4, 5 in the P block, 3p5 gets us to chlorine. That makes total sense, right? Because 5 and 2 makes 7. So there are 7 valence electrons for chlorine because it's column 7, okay? And that's its configuration, okay? This is the argon core. So we can write the condensed if we wish. And that's the big trick. If you take anything away from this, you know, probably the most important thing is being able to read across the periodic table to the position where the atom you want its configuration is, and then being able to kind of construct its configuration. Okay, so you don't have to translate boxes to configurations anymore. In fact, what I suggest you do once you've mastered this is translate it backwards, right? So if I ever ask you for a box diagram, do the configuration and just put it in the boxes. Okay, so let's look. Lithium, element number 3. If I look at where lithium is, right, I can kind of say, well, it's in the second row and it's in column 1, so that's the S block, so it's 2s1 as its final configuration. Yeah, all right, so lithium 1s2 gets me to here, 2s1 gets me there. That's the helium core, right? So I can write helium 2s1. All right, what I suggest you do, there's a bunch more. Try them, right? There's a hint for selenium on the next page. It's a bit like this if you want to peek, right? Okay, but try them, right? Look at the periodic table. Look where aluminum is, right? Aluminum is the first element in the P block in the third row. So that terminal electron is going to be 3p1, isn't it? So it's going to finish 3p1. So all the way up to 3p1 for aluminum. Okay, give you a second, try those. I'll write them out. Okay, aluminum, all the way up to 3p1. So 1s2. Let's kind of run it down. So 1s2 gets me to helium. That's just right where aluminum is, right? Aluminum is there, right? 2s2 gets me to beryllium. 2p6 gets me to neon. 3s2 gets me to magnesium. And then one more. Oh, that's 3s2, my mistake, 3s2. And then 3p1 gets me to aluminum. Okay, what's my shorthand for that? Well, again, that's the argon core. Sorry, that's the neon core. Neon, 3s2, 3p1. Okay, now I mentioned there's a hint there. You can flip over and you can see that, right? So maybe I'll use the hint. Okay, so for selenium, all right, selenium, there's selenium, right? So it's in the 1, 2, 3, 4th row, 4th one in the P block. So its last electron is 4p4. So all I've got to do to get selenium is just read all the way up to 4p4, right? So hopefully this is more familiar now. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and this is the first one where we've seen some transitions. So there's 10 boxes because remember 5 orbitals, 5 different directions, 2 electrons per orbital, so 10 boxes. So that's 3d10 to get to zinc. That's where zinc is, 3d10. And then 1, 2, 3, 4, 4p4. Okay. Now remember, the nearest noble gas before is argon, and what's on top? Well, everything in the 4th row and the 3Ds, so 4s2, optional 3d10, 4p4. Okay, 4, 5, 6 valence electrons, column 6. All right. Now, xenon, if I write it, is here. Okay. Now I'll tell you a little story, right? So, I don't know if any of you go to or used to go to Plainfield Central High School, right? Okay, my son was taking a chemistry class down there, and his turn to go up to the board, and he had to write the electronic configuration of xenon, and this is what he wrote. Okay, 1s2, 2s2, 2p6, 3s2, 3p6 to argon. Okay, 4s2, 3d10, 4p6. It's all the way down here, right? It's in the 5th row, so I can keep going. 5s2 gets me to here, 4d10, and then 1, 2, 3, 4, 5, 6, 5p6. It's in the 6th row, right? And it's in the 6th spot in the block, right? So its terminal electron is 5p6. And then the follow-up question was, what's its condensed version, right? And this is what he wrote. He wrote, it's going to be that one there, one up from, that's krypton, right? And then the valence layer, 5s2, 4d10, 5p6. And that's what he wrote on the board. And he was 100% correct, because his dad taught him how to do it. Teacher graded him wrong. It came back with that. That is a smug, smart-ass way to do this, which does not make any sense, which I expressed in an email. Okay, the valence layer, full or not, is still the valence layer. Okay, for xenon it actually does chemistry, so you have to write it. You never get smug and write the noble gas as a noble gas just because it's got a full outer layer. No, the full outer layer is still there as an outer layer. Okay, so you've got to write it. Definition: core and valence. Valence can be full, it can be partially full. Doesn't matter. As long as it's on the outside, you've got to write it. So don't be like Plainfield Central. Okay. All right. All right. Now, as we mentioned then, S, P, D, and F elements, why are they so named? Because this is the S block, the P block, and the D block. Zinc, for example, 3d10, its last electron is a d electron. It's a d element, right? It's a d block element. We just saw xenon. Its last electron was 5p6. It's a p block. Maybe it's sodium, right? Up here, sodium. Its electron 3s1, s block, so it's an s block element. So wherever the last electron goes, whichever block it's in, that's what defines it as an element, right? So S, P, and D are so named because the elements are, their last electrons are there, and that's their position if you think about it in the periodic table, okay? So anything in the center region is a D block element, anything in this left two is an S block, anything in here is a P block. And if you look at the old periodic table, right, there's actually a little arrow that points there. The periodic table is actually much wider because this actually sits in here, right? But it doesn't fit on the page, right? So this actually fits in here. It's not usually shown in periodic tables, but that would be the F block, which is two more, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Actually 14 wide, right? 14 wide. Okay. All right. Now, more extra credit. Where did S, P, D, and F come from? Okay. Originally, okay, what's the original origin of S, P, D, and F? Okay, +1, Tuesday. All right. All right. Now, we're nearly done, right? So at the end of this packet, you should be able to do a box diagram, do an electronic configuration, and an analogous dot diagram, okay? So, let's go through them, right? So what I suggest, to be honest, because you now know how to read across the periodic table, use that skill to create the electronic configuration first, and then turn it into a box diagram, all right? And then turn it into a dot diagram. So first, second, third, right? Okay, so what I'm going to do actually is I'll give myself a little reminder here, all right? What I'm going to do is actually give you two of these, right? So let's do fluorine, and let's maybe do sodium. Okay, so we'll do fluorine and we'll do sodium. And then the remaining three, right, just scan this to me and send it me back for extra credit, right? And I'll give you like a point per row, right? So fluorine, electronic configuration, be careful, you've got to put that, right? Let's read across, right? So fluorine, if you look in the back of the book, I actually have a really nice periodic table with the electronic configuration shown for each element, right? If I can find that. I had it lurking somewhere. Actually, I think it's over here. Actually, if you look in the back of the packet, you'll find it, right? I misplaced it, but anyway, I'll with the power of the internet, I'll throw it up for you. Okay, all right. But you can, you can look at periodic tables with electronic configurations actually in the box, right? Or better, just read across, right? Just read across. So, if I look at fluorine, what's this terminal electron? Well, it's row 2, P block, fifth one over. So 2p5 of its last electron, and then it's going to build up 1s2, 2s2, 2p5. All right. 1s2, 2s2, 2p5. Just read across the periodic table. Orbital box diagram, fluorine. There's my 1s. There's my 2s. There's my 2p, and I've got 2 in there. 1, 2. Do not put 2's down here. Don't, because they're 2, right? Those 2 are these 2. That 1s is an address, right? And then 2 in there, 1, 2, and then 5, 1, 2, 3, 4, 5. Does it match its dot? Of course it does. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 on the inside, 3 pairs, and a single. We saw that kind of before, didn't we? All right. Sodium. Sodium is the first element in row 3, so 3s1 is its terminal electron. So let's read across. Sodium, 1s2, 2s2, 2p6, 3s1. Fair enough. Sodium, 1s, 2s, and just draw the number of boxes you need, right? So I don't need all the boxes for the parking lot, just the ones I need. I need up to 3s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sodium's number 11, right? There we go. Sodium, what's it look like? 2 full layers. And then 1 extra. So that's the core, that's the valence. There we go. You can write it condensed here if you want. Okay. Do you notice any similarities? Same question again, right? So the box diagram matches here, right? Matches. Okay. So again, do these 3, get them to me by end of Tuesday for some good old extra credit. Okay. All right. Now, it's got literally 1 page left. I'm just going to pause a second because I'm literally out of time again. Just pause and come back real quick. Okay, see you in a second. Okay, now, should this have been the regular semester, I'd have given you a take-home assignment, right, which is worth a little bit of extra credit. All right. Unfortunately, I can't send you home with a piece of paper. So I'm just going to show you what I'm talking about here, okay? I mentioned it before, and this normally isn't covered, right? Okay, it's usually saved for like a 300 level course. But I'm going to show you where the dot diagrams and the box diagrams break down, okay? All right. So what I want you guys to do, if you want to think about it, so draw an orbital box diagram and sketch the dot diagram for carbon. Okay, so for carbon, right? So let's do the box diagram first. So it's got 6 electrons, it's carbon number 6, right? So 1, 2, 3, 4, 5, 6. Fair enough, right? Okay. Now, when I do my, and I'll do it over here, when I do my dot diagram, I do my points of a compass, and look, I've got 4 single electrons on the outside, but in here, I've got a pair and 2 singles. That would look like this. A pair and 2 singles. That's horribly wrong. So why is this not right? This is called the ground state electronic configuration, right? Okay, it's what the atom would look like in terms of where its electrons are if it was just an atom by itself floating off there in space somewhere, okay? But it turns out that in nature, oh, it's my old timer, right? In nature, if you make a bond, remember making a bond creates energy, right? So I can use the bond creation energy to promote electrons. It's kind of interesting, right? And this is what I would have shown you in your class, right? So if I look at carbon, right? So here's an energy level diagram. So there's my 1s, 2s, 2p, 1, 2, 3, 4, 5, 6. That's its ground state configuration, right? But when I look at carbon as a dot diagram, which is an accurate description of how it is in nature, it's got 4 on the outside and 2 on the inside. So what's happened is that electron's been promoted up to there, right? And this is called the bound state, right? If I look, I have 4 unpaired electrons compared to 2. Now remember, what's a covalent bond? It's a shared pair of electrons, right? 1 from each atom, right, combines the pair. So these will go off and make 4 bonds rather than only 2. I get literally twice as much energy back if I make 4 bonds rather than 2. And the energy I get back far exceeds this little gap. It's like me saying to you, hey, I'm going to give you $5 right now. Sorry, no, let me rephrase that. It's like me saying to you, hey, lend me $5 right now and absolutely 100% ironclad guarantee I'll give you $100 tomorrow. You going to do it? Well, yeah, because you're going to make $95, right? And that's exactly how nature is. So nature, if you like, can borrow energy, right? So it borrows a little bit of energy from making bonds to promote electrons, right? So if you've got to be in the same layer, that's the trick. It's only within the same layer because the gap's short there, right? If I can promote an electron to make more unpaired, bang, I can do it, and it's a more stable system. So that's why the dot diagram does not look like the ground state, but it does look like what we call the bound state. Okay, now that happens for columns 2, 3, and 4, right? So I've been careful trying not to show you examples from columns 2, 3, and 4 because they have different ground and bound states. Turns out that the ground and the bound state is identical for everything except columns 2, 3, and 4. Okay, all right, so let's do it here. So the bound state is 1s, 2s, 2p, 1, 2, and the 1 gets promoted, right? There it is. Oh, that's this. There. 1, 2, 3, and 1. So that's 4, right? So that's what that is there. Okay. So bound state configurations for columns 2, 3, and 4 are different than the ground state configurations, and that's the only columns where that applies. Okay. So, for example, if I did beryllium, if I look in the periodic table, beryllium is element number 4, right? So it should have just 4 electrons. 1, 2, 3, 4. If that were how beryllium was in nature, it would not make any bonds at all. It wouldn't lose any electrons because it's stable, right? Okay, so what it does, it promotes one of them. Beryllium column 2 makes a +2 ion, it loses those 2 electrons, right? Okay, but it has to be promoted to make a bond, so to speak. Okay, so as I mentioned, they have different ground and bound state configurations. You have to spend money. That cost me $5 to make money. I get a bunch of energy back there. Okay, all right. So that's why, you know, we see that. Okay. Now, finally, we can look at this one. I'll do maybe a couple. You've seen these before, okay? I've actually chosen a couple of the same from the previous packet just to show you kind of how this works, right? So when I have the oxide anion, it's 2 extra electrons, isn't it? Right, so when I do my box diagram, it's going to be 1s, 2s, and if I think about it, if I look at my periodic table, oxygen is here, so I need the 2p block, right? Okay, I don't need anything past that. Okay, now if I did oxygen, 1, 2, 3, 4, 5, 6, 7, 8, fair enough, right? But oxide is a -2 ion, right? Okay, guess what? 2 extra electrons come in, where do they go? They fill here and here. So now that's completely full, right? It looks like neon, yeah. So it's an inert gas configuration. Remember, atomic ions look like a noble gas. I have to add 2 to get the full box, right? If I go the other way, oh, let's write the configuration. This is why, you know, you should just know 1s2, 2s2, 2p6. It's isoelectronic with neon. All right. The other one should be straightforward, but I want to do the other cation, right? Okay. So magnesium is an Mg2+, right? It's going to have its final configuration 3s1, 3s2, but it's going to miss 2 electrons because it's +2, so it's going to go all the way back to neon. So I'm just going to do the neon configuration all the way up to 2p6. So maybe I'll do this one the other way around. So 1s2, 2s2, 2p6, that's 6, 7, 8, 9, 10 electrons. Magnesium number 12, I've lost 2, right? Okay, if I do that as a box diagram, what does it look like? It looks just like O2-, right? Oh, almost did the error there. 1, 2, 3, 4, 1, 2, 3, 4, and then 6. 1, 2, 3, 4, 5, 6. So it's lost the ones from here, right? It will be 3s2 there, okay, but it's not there because 2 electrons were lost. Okay, these guys, just like we did before, they're just atoms, so you can do that. This is a practice exam question, all right? So if you can do these, those are the trick questions, all right? I'm pretty confident you can do those. Remember, you are going to hopefully send me this for extra credit, and that'll be great practice. Okay. All right, so that's the end of the packet. Hopefully that makes sense. Okay, the exciting world of quantum mechanics. Stop there. See you next time.